Welcome back to the 5th lecture in our Random Forests series. In this video, we're going to explore how random forests can be used to estimate and impute missing values in a dataset. In the previous 2 lectures, we spent quite a bit of time discussing the out-of-bag score and how it can be used to evaluate random forest models. In this lecture, we'll move on to another important concept known as the proximity matrix, and we'll see how it can be used to handle missing data. We'll begin by understanding what the proximity matrix is and how it is constructed. Then we'll use it to estimate missing values in training samples. Let's start with a very simple example dataset. Let's say we have a dataset with 4 samples. Each sample contains 4 features, represented by X and a target variable, Y. The 4th sample has missing values in the 3rd and 4th features. Our goal is to construct a proximity matrix using random forests and then use that matrix to estimate these missing values. This example is adapted from the reference video shown below. The basic idea is very intuitive. To estimate a missing value, we look for other samples that are similar to the sample containing the missing value. For example, sample 4 is very similar to sample 3. 2 of their feature values are exactly the same, and they also share the same target label. Because of this similarity, it's reasonable to expect that the missing values in sample 4 should be close to the corresponding values in sample 3. This is the basic idea behind estimating missing values. To measure similarity between samples, random forests use what is called a proximity matrix. A proximity matrix is essentially a measure of similarity between data samples. Since similarity is the opposite of distance, the quantity 1 minus the proximity matrix can be interpreted as a distance matrix. Now let's see how the proximity matrix is actually constructed. The first step is to assign rough initial values to the missing entries. Let's begin with the 3rd feature, which is a categorical variable. For categorical features, the initial value is usually chosen as the most frequent category. The target label of sample 4 is no. Therefore, among all training samples whose target label is also no, we look at the 3rd feature and find the most common category. In this example, the most frequent value is no, so we use that as the initial estimate for the 3rd feature of sample 4. Next, let's initialize the 4th feature, which is a continuous numerical variable. For numerical variables, the initial estimate is typically the mean or the median. Among all samples whose target label is no, we compute either the median or the mean of the 4th feature and use that value as the initial estimate. In this example, the average value is 167.5, so we use 167.5 as the initial estimate. At this point, the dataset no longer contains any missing values. So we can train a random forest model using this temporarily completed dataset. Let's assume that our random forest contains 10 trees. After training, we pass all samples through each tree. Let's say the first sample falls into leaf node 3 in tree 1. And the second sample falls into leaf node 0. We repeat this process for every sample and every tree, recording the leaf node assignment for each sample. This table shows the leaf node assignments for all samples across the trees. Fortunately, obtaining these leaf node assignments is very easy in Python. In scikit-learn, the apply method of a random forest model returns the index of the leaf node that each sample reaches. Here, samples 3 and 4 fall into the same leaf node in tree 1. In tree 2, samples 2, 3, and 4 all end up in the same leaf node. When two samples land in the same leaf node, it suggests that the tree considers them similar. The more frequently this happens across different trees, the more similar the samples are. Now let's turn this table into a proximity matrix for each tree. The proximity matrix is a square matrix whose rows and columns both correspond to data samples. Let's look at the proximity matrix for tree 1. Since samples 3 and 4 fall into the same leaf node, we place a value of 1 in the cell corresponding to row 3, column 4. Likewise, we place a value of 1 in row 4, column 3. These entries indicate that samples 3 and 4 share the same leaf node in tree 1. The Python code shown below can generate this matrix very easily. Here, the variable t represents the first column vector from the leaf node table. Normally, all diagonal entries of a proximity matrix would be equal to 1. Because each sample is perfectly similar to itself. Later, we'll use this matrix to estimate missing values. But if we keep the diagonal entries equal to 1, a sample could influence its own imputed value. To avoid that, we set all diagonal entries to 0. This prevents a sample from contributing to its own imputation. For tree 2, 3 samples share the same leaf node, so the corresponding proximity matrix looks like this. For tree 3, 2 samples share a leaf node, producing another proximity matrix. Next, we simply add together the proximity matrices from all trees. The resulting matrix looks like this. Here, the entries in row 3, column 4, and row 4, column 3 are both 3. This means that samples 3 and 4 fall into the same leaf node in 3 different trees. Since these are the largest values in the matrix, we can say that samples 3 and 4 are the most similar to each other. Now, let's extend this to all 10 trees in the forest. The resulting matrix might look something like this. Here, the entries in row 3, column 4, and row 4, column 3 are now 8. In other words, samples 3 and 4 share the same leaf node in 8 out of 10 trees. This indicates a very strong similarity between the two samples. The next step is to normalize the matrix. One option would be to divide every entry by the total number of trees. However, we'll use a different normalization scheme. We'll normalize each column so that the sum of every column becomes 1. This makes the subsequent calculations much more convenient. This is the proximity matrix after the first iteration. Later, we'll repeat this process multiple times. Now that we understand how the proximity matrix is constructed, let's use it to estimate missing values in the training samples. Recall that the proximity matrix obtained from the first iteration looks like this. and the initial estimates for the missing values are shown here. Let's begin with the numerical feature weight. The weight feature vector is shown here. And this is the column normalized proximity matrix we just constructed. Now let's multiply the weight feature vector by the proximity matrix. The result is the vector shown here. The resulting vector gives the new weight estimates. Since we're estimating the missing value for sample 4, we're only interested in the fourth element of this vector. We use this value as the new estimate for the weight feature of sample 4. As a result, the value in this cell is updated from 167.5 to 198.5. After updating the value, we retrain the random forest and generate a new proximity matrix. We then use the new proximity matrix to update the estimate again. We repeat this process until the estimate converges and no longer changes significantly. Now let's see why this works. The column vector extracted from the proximity matrix can be viewed as a set of weights. Since sample 4 is highly similar to sample 3, the third weight is the largest, with a value of 0.8. In other words, sample 3 contributes the most to the estimated value for sample 4. Essentially, we're taking a weighted average based on sample similarity. Samples that are more similar receive larger weights, while less similar samples receive smaller weights. As a result, the estimated value is influenced primarily by the most relevant neighboring samples. This is how continuous numerical variables are imputed using the proximity matrix. The methods we've described so far are for classification problems, but the way we obtain the initial estimates is slightly different for regression problems. In classification, we can use target labels to obtain better initial estimates. In regression, however, the target is continuous, so we cannot use target values for grouping. Instead, we typically use the overall mean, median, or mode as the initial estimate. After that, the update process is the same. Numeric features use a similarity-weighted average, and categorical features use a similarity-weighted vote. Next, let's see how categorical variables are handled. Let's look at samples 1 through 3, excluding sample 4. In this feature, the category no appears twice, while yes appears once. Now for each category, we simply sum the similarity weights from the fourth row of the proximity matrix. Only sample 2 has the value yes, so the total weight for yes is 0.1. Samples 1 and 3 have the value no, so the total weight for no is 0.1 plus 0.8, or 0.9. Since the total weight for no is larger than that for yes, we estimate the missing value as no. After each update, we retrain the random forest, construct a new proximity matrix, and estimate the missing value again. We repeat this process until the estimates stabilize. Let's briefly summarize what we've done so far. For numerical variables, we use the proximity matrix to compute a similarity-weighted average of observed values. For categorical variables, we sum the proximity weights for each category and select the category with the largest total weight. After updating the missing values, we retrain the random forest and generate a new proximity matrix. By repeating this cycle, the estimates gradually improve and eventually converge. This is the core idea behind using random forest proximity matrices to impute missing values in the training data. So far, we've focused on imputing missing values in training data. However, if the test data also contains missing values, the imputation process is slightly different. For training data, we can take advantage of the target labels because they are available. In test data, however, target labels are not available, so we need to use a different approach. We'll cover this in detail in the next video.